Hello everybody. In this video we're going to be writing the Lewis dot structure for diatomic oxygen. The first thing like we always do is write down which atoms we have. We only have one type. We have oxygen here. Next we need the electron configuration for oxygen. I'm going to come down to the table that we used here. And this time what we're going to be looking to do is to find oxygen, which is right here. We know the valence portion is going to be 2s2, 2p4, and then we're going to come up and over, so it's going to have a core of helium. We're going to come up here, so we have our helium core, 2s2, 2p, 2p4. This is a main group element, so we need to be looking for the highest n order, which they're both the same, they're both 2. That means that we can just add these subscripts together and determine that oxygen has 6 valence electrons. It always will. Next we need to figure out our bank. So I have 2 of these oxygens, so 2 oxygens. Each one of them is going to give me 6 valence electrons, so I have a total of 12 valence electrons in my bank. The next step is going to be to write a skeletal representation of this. We only have 2 atoms, so they must just be connected to each other. So I'm going to have an oxygen bound to another oxygen. I formed a bond in doing that, so I had 12 electrons in the bank minus 1 bond's worth of electrons. Each bond is going to require 2 electrons. I have 10 electrons left in the bank. These 10 electrons are going to need to be placed onto these 2 atoms here. We can do that evenly, so if we have 2 atoms and 10 electrons, they each get 5. So let's do that. We have oxygen, a bond, another oxygen, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now that we've done that, we need to look at the octet here. So from this oxygen's perspective, he gets 1, 2, 3, 4, 5, 6, 7. From this oxygen's perspective, it's the same as this one, 1, 2, 3, 4, 5, 6, 7. So each of them wants to have one more electron. I think the easiest way to kind of conceptualize this is a little bit different than some of our previous examples. I'm going to imagine this one electron comes down and this one electron comes down. So each of them is sharing one of their electrons with the other one. Now, if I rewrite my result after that, I now have a double bond. Each of these guys still has 2 lone pairs on it. And I redo my count. From this guy's perspective, he has 1, 2, 3, 4, 5, 6, 7, 8. Again, from this guy's perspective, 1, 2, 3, 4, 5, 6, 7, 8. And now we are happy. And we have the correct structure. Now, let's think about what would have happened if we hadn't done 1 and 1 this time over here. So we're just going to give ourselves a little bit of a scratch area over here to just think about things. Okay, we already have our answer. We're going to start from here. And I could imagine taking this lone pair and placing it up there. I would now have this double bond here. There would be 3 dots remaining on this guy and 5 dots remaining on this guy. Now I can do my count from this guy's perspective. He has 1, 2, 3, 4, 5, 6, 7. Still missing an electron that it wants. From this guy's perspective, he has 1, 2, 3, 4, 5, 6, 7, 8, 9. He has 1 too many electrons. And, you know, I see people who get to this point and then they're just real confused. And I think that the best way to kind of conceptualize that is just the idea that, you know, maybe we could have thought about it differently somewhere around here. Maybe there was some little mistake somewhere. But really, this guy's just missing an electron, and this guy has an extra one at this point. So all we really need to do is just take one from this guy and place it over here. And then we wind up with the exact same solution that we did before. Each of these guys has 2 lone pairs, 1, 2 lone pairs, 1, 2 lone pairs, and a double bond in between. This is kind of the preferred way to write that too, with the lone pairs as far away from each other as possible, as opposed to being on top of each other here. But it's still the exact same conclusion. This structure is the same as this structure here. It's never a bad idea to write your final answer out like that in a nice, clean, clear way. But as just a little lesson, you know, if you get to this point where one guy just has extra electrons and the other one doesn't have them, just give it to him. You know, it's not going to be a problem. You're still going to come back to the same conclusion. And we could think about that even another way. If we come down here and do another little example down here, I originally started with something that looked like this, right up here. I decided I still had 10 electrons, and I gave 5 to each one. But I didn't necessarily need to do that. I could have done that kind of asymmetrically from the get-go and just kept them always as pairs. It's not a bad strategy at all. So I could have given one of them 6 and the other one 2. Okay, now if I do my count, I got 1, 2, 3, 4, 5, 6 for this guy. He's missing 2 electrons. This guy is 1, 2, 3, 4, 5, 6, 7, 8. He's happy already, right? He needs to share some electrons with this guy. So I'm going to imagine this pair here coming down. And then when I rewrite this, I come back to the exact same conclusion that we had before. So the lesson here is that there are a few different pathways you can take when you're trying to write out your Lewis dot structures. Just we have to remember the things that we need them to have. You know, we need to pay attention to where all the dots are, all the electrons are going. We need to make sure that they have their octet. We can't be afraid to shuffle things around if we need to. And, you know, we can set things up in different ways and still always come to the exact same conclusion, which some students find a little disconcerting sometimes. They want one really clear way to do it each and every time, but this just isn't really one of those things. You can think about it multiple different ways, and so long as you're following through with the same correct steps, you're going to come to the same conclusion.